One of the basic earth-abundant elements that we must learn to properly manage is iron. It is our goal to gain an understanding of the chemistry and energy related to the circular sustainability of the element known as Fe. This symbol is derived from the Latin word for iron, ferrum. Iron is a metal with an atomic number 26. The Recovery 2.0 system is an innovative approach to manage the treatment of residual waste materials, in a sustainable method by treating waste as a resource, while assisting with the world's demand for clean water and clean energy by using thermal reduction. Within the Recovery 2.0 process, we have focused a great deal of effort on energy recovery in an effort to manage the energy continuum while attempting to maintain a balance or equilibrium with our environment. We commonly encounter iron in the form of scrap and as rust and residues mixed into various waste streams, but is typically prevalent as a fraction of electronic wastes. Sorting iron content scrap is typically performed with the use of a magnetic separation system. This segregates the clean iron and steel scrap into a saleable raw commodity feedstock. One possible handling pathway option involves the separation of the scrap iron, sorted into a fines fraction that accumulates the fine iron particulates, rust, and residues together. The potential to convert this dirty fraction into a premium refined product exists, while at the same time extracting the chemical energy contained within the iron elements. Using the iron fines as a reactant, it is possible to harness the molecular bond energy or chemical energy. The chemical redox reaction of oxidation releases energy in the form of heat and/or electricity. The harvesting method or device used determines the mix of energy recovered. The choice of more heat from combustion, or more electricity derived from a fuel cell may be designed. A sliding scale combination of heat and electricity may be designed into a redox reactor system. The energy from the oxidation of iron may also be harnessed by utilizing an iron-air battery. Renewable or surplus electricity may be used to regenerate or recharge the iron battery. The option to design a regenerating flow battery system exists. An additional method of harvesting energy from iron may exist with an iron and steam production process of producing hydrogen or H2. This process oxidizes the iron and reduces the steam into a captured hydrogen gas. The various types of iron energy generation typically render the iron in the form of an iron oxide. The reduction of iron oxide into a purified refined iron is not a new challenge. One of the traditional methods of reducing iron ore into refined iron is with the use of a blast furnace process. This process has been a legacy source of CO2 emissions. The search is on for alternatives to produce iron with a reduced carbon footprint. The production of green steel converts iron oxide with the use of hydrogen, while avoiding the generation of CO2. This process produces direct reduced iron, referred to as DRI, or sponge iron. An alternative option for the reduction of iron oxide to produce a purified iron product is with a method of displacement, using some variation of a controlled thermite reaction. As an overview of the realm of iron chemistry and energy, it is possible to convert iron fines, residues and oxides into a refined iron product that may become a cornerstone or key part of a regenerative energy cycle. We intend to discuss additional facets of the commodity and energy recovery sectors at some point in the future. Until then, please feel free to contact us at your convenience. Recovery 2.0 is a project developed by Waste.net, in an effort to reinforce our belief that as rational human beings, we must accept the ultimate responsibility to leave future generations with a safe and sound environment, and a world that has not been depleted of its resources. Please feel free to visit us today at www.waste.net.